In our atomic unit and potentially in first year chemistry, we got a good introduction and or review to the importance of light and the electromagnetic spectrum in our understanding of chemistry. The visible light and the color of objects or the color of light that they give off is super important in terms of understanding the structures of things, whether it be an atom or an ion by itself, a molecule and thinking about how it's bonded, or even a solution or mixture. So there is a connection we have already established between what the electrons are doing, where they are within energy levels, and how light can come in and out. But there are other connections with electromagnetic radiation that are important that connect to the topics we've looked at recently. So here we have an electromagnetic spectrum. Across the top, I have wavelengths, and across the bottom, I have frequencies. I have kind of the general labels here with some estimates as to their frequencies and wavelengths, and I have some general labels over here. You won't need to know exact values for any of these, but just understanding that the lower or higher the energy is, the more we can understand what it would do. We did talk about photoelectron spectroscopy, which uses X-rays and ultraviolet rays to actually remove an electron from the atom. Here we're focusing on the different forms of energy that would be a little bit lower. So starting down here near the bottom, microwaves in terms of their understanding of atoms, molecules, and electrons are fairly low energy. They are not energetic enough to cause electrons to move between levels, but they are energetic enough to cause molecules to spin if they're able to spin. So microwave radiation is helpful in terms of us understanding bond order. Single bonded atoms, as we've talked about before, are able to spin. But with the way pi bonding works in double and triple, we cannot spin those bonds. So by using microwave radiation, we can kind of explore, are bonds spinning or are molecules spinning or not, and know a little bit more about whether it's single, double, or triple bonds. Slightly higher energy is needed to get molecules to vibrate. So molecular vibration is taking our atoms that are at a certain defined length from one another based upon their attractions and getting them to vibrate in and out. That takes a little bit more energy than just spinning because we are overcoming the attraction and then it comes back in. So just like there's energy levels for electrons, there's energy levels for spinning and energy levels for this vibration. We can see how well things vibrate or think about their bond strength and the types of bond by looking at infrared radiation. This is something you will do a lot of if you go on into organic chemistry. The IR fingerprint is super important in understanding the different atoms, the different bonding, and the different functional groups in organic molecules. The one we already looked at is visible and ultraviolet radiation. So kind of my rainbow here going up to ultraviolet. And here we go red to blue or red to violet in terms of my colors. That is enough energy to cause electrons to move between levels. So we can jump up to a higher energy level or come back down to a lower level. All three of these connect to, importantly, the photoelectric effect. The photoelectric effect applies our understanding that light can act as a particle and particles can act as a wave, or more directly, that when an electron absorbs a photon or an amount or a quantum of energy, then that atom, molecule, ion gains a certain amount of energy that's exactly equal to the energy of that photon. When it then falls back down and it releases a photon, that's the energy change that it underwent. It's very important because that is what allows us to know those energy gaps, whether it's an energy gap in the visible or ultraviolet range between energy levels, whether it's an energy gap in terms of vibration and infrared, or whether it's an energy difference in terms of maybe spinning something in a rotational. So over here, we're kind of seeing that when I do this, my rotation doesn't cause big differences in my internuclear separation. But for a vibrational energy level there, This is showing that I've got a nucleus right here. It could go all the way either this close or that far away if we've gained that much energy. We could also take electrons that are in a certain energy level and jump them to a higher energy level from level 2 to 3, even when they're involved in bonding. So all of these different things have wavelengths and frequencies associated with those energy changes. The two equations that help us to make those calculations or to quantify those things are the speed of light, c, is equal to lambda times nu, wavelength and frequency. In the equation, these are in meters and hertz, but sometimes you are presented with a wavelength in nanometers as we are down here, which we will practice. And then we've got our energy. It can be in kilojoules, but within this equation, we want it to be in joules. When we do that, we've got energy is equal to HV. H is Planck's constant, a tip of the cap to the physicist and chemist who discovered the idea of the quantum of energy, or the smallest piece of energy. So we have frequencies related to energies, energies to frequencies, frequencies to wavelengths, wavelengths to frequencies, or we can put these two given equations together to apply.